Welcome! In this session, we'll explore problem number 1800, maximum ascending subarray sum. This is an interesting array-based problem that challenges us to find the maximum sum of ascending subarrays. Let's dive in and understand the problem, break it down, and solve it step by step. The problem requires us to find the maximum possible sum of an ascending subarray in a given array of positive integers. A subarray is a contiguous sequence of elements within the array, and an ascending subarray is one where each element is strictly greater than the previous one. For instance, in the array nums equals 10, 20, 30, 5, 10, 50, 10, 20, 30 is an ascending subarray because each number is larger than the one before it. The goal is to calculate the sum of all such ascending subarrays and return the largest of these sums. The input will be an array of positive integers, and the output will be a single integer representing this maximum sum. Let's look at the first example. For the input nums equals 10, 20, 30, 5, 10, 50, the ascending subarrays are 10, 20, 30, and 5, 10, 50. The sum of 10, 20, 30 is 60, while the sum of 5, 10, 50 is 65. Among these, the maximum sum is 65, so the output for this example is 65. In this case, identifying the ascending subarrays and comparing their sums allows us to determine the result. In the second example, the input is nums equals 10, 20, 30, 40, 50. Here, the entire array is an ascending subarray because each element is greater than the previous one. The sum of this subarray is 10 plus 20 plus 30 plus 40 plus 50, which equals 150. Since there are no other ascending subarrays to consider, the output is simply 150, the sum of the entire array. Now, consider the third example with nums equals 12, 17, 15, 13, 10, 11, 12. The ascending subarrays here are 12, 17, and 10, 11, 12. The sum of 12, 17 is 29, while the sum of 10, 11, 12 is 33. Among these, the maximum sum is 33, so the output for this example is 33. This demonstrates how we need to identify and evaluate each ascending subarray to determine the result. Finally, let's consider some edge cases. If the array contains only one element, such as nums equals 5, the output is simply the value of the element itself, which is 5. If all elements in the array are the same, such as nums equals 5, 5, 5, 5, no ascending subarray exists, so the output is the largest single element, which is 5. For a strictly decreasing array like nums equals 100, 90, 80, 70, each element is its own ascending subarray, so the maximum sum is the largest element, 100. In cases where multiple ascending subarrays have the same sum, such as nums equals 3, 5, 2, 6, 4, 7, the maximum sum is derived from any subarray with that maximum value, such as 3, 5, or 6, 7, both of which sum to 13. These examples highlight the importance of carefully handling edge cases while solving the problem. To approach this problem, we first consider the brute force method. The intuition here is straightforward. We generate every possible subarray from the input array nums and calculate its sum. For each subarray, we verify if it is ascending by checking that each element is strictly greater than the one before it. Once we confirm a subarray is ascending, we compute its sum and keep track of the maximum sum encountered. However, the complexity of this approach is a significant drawback. Generating all subarrays takes O(n) squared, and for each subarray, we may spend up to O(n) verifying its order and calculating the sum. This results in an overall time complexity of O(n) cubed, which becomes highly inefficient as the size of the array increases. To address this inefficiency, we turn to an optimized sliding window approach. The key idea here is to process the array in a single pass while maintaining a running sum for the current ascending subarray. As we iterate, if we encounter a break in the ascending sequence, where nums I is less than or equal to nums I1, we compare the running sum with the maximum sum recorded so far, reset the running sum to the current element, and continue. By the end of the array, we ensure the final subarray is accounted for, making this approach far more efficient. The sliding window approach is highly efficient in terms of complexity. Since we only make a single pass through the array, the time complexity is O(n). Additionally, because we don't use any extra data structures and only maintain a few variables, the space complexity is O(1). Several key observations about the problem enable this optimization. First, an ascending subarray is defined by contiguous sequences where nums I is greater than nums I1. This means we don't need to generate subarrays explicitly, instead, we can calculate sums incrementally as we traverse the array. Second, by resetting the running sum whenever the ascending sequence breaks, we ensure that only valid subarrays contribute to the computation. These insights allow us to avoid redundant calculations and make the process more streamlined. Given these advantages, the sliding window approach is our chosen strategy. It effectively leverages the nature of the problem, achieving linear time complexity and constant space usage, which are critical for handling larger arrays efficiently. This makes it significantly better suited than the brute force method, particularly when performance is a concern. When comparing the two approaches, we can see clear trade-offs. The brute force approach is easier to conceptualize because it involves explicitly generating and examining all possible subarrays. However, this simplicity comes at the cost of performance, as its cubic time complexity makes it impractical for large input sizes. On the other hand, the sliding window approach offers both time and space efficiency, processing the array in linear time with constant space. The trade-off here is that it requires careful implementation to ensure the running sum is properly tracked and reset at the right moments. While alternative methods like dynamic programming might come to mind, they are unnecessary for this problem since the sliding window approach already achieves optimal performance with minimal complexity. In conclusion, the sliding window method strikes the perfect balance between simplicity and efficiency. It avoids the pitfalls of brute force while delivering the best possible performance, making it the most effective solution for this problem. To solve this problem, we need to focus on identifying subarrays within the input array nums that are strictly ascending. A subarray is simply a contiguous segment of the array. For example, in the array 1, 2, 3, subarrays include 1, 2, and 2, 3. The goal is to iterate through these subarrays, check if they meet the condition of being strictly ascending, and then perform a specific computation, such as summing the elements. The brute force approach involves systematically considering every possible subarray, validating whether it is ascending, and calculating the sum if it is. This gives us a clear path to break down the problem and ensure we capture all valid subarrays for computation. Now, let's outline the brute force algorithm to solve this problem. First, we use an outer loop to iterate over all possible start indices of the subarrays, denoted as I. Then, for each start index I, we use an inner loop to iterate over the possible end indices j, ensuring that j is greater than or equal to I. For every subarray defined by the indices I, j, we check if its elements are strictly ascending. This means comparing each element in the subarray with the previous one to ensure that each value is greater than the one before it. If the subarray passes this check, we perform the required computation, such as summing its elements and adding this value to a result variable. Once all iterations are complete, the final output is returned, which represents the cumulative result of all valid subarrays. After completing the nested loops, the cumulative result is stored in the variable result, which is then returned as the output. Understanding the key insights can help clarify the efficiency and behavior of this approach. The brute force algorithm performs two nested iterations over the array to identify subarrays, resulting in n² iterations. Additionally, checking if a subarray is ascending requires iterating through its elements, which can take n in the worst case. This means the overall time complexity is n³. Space complexity, however, is 1 if computations are done in place without storing subarrays explicitly. It's also crucial to handle edge cases, such as an empty array, where the result should be 0 as no subarrays exist, or an array with a single element, which always qualifies as ascending. Arrays with all elements equal or arranged in descending order have no valid subarrays, so the result in such cases is also 0. The algorithm primarily uses basic data structures, such as a variable result to store the cumulative computation and two nested loops for iterating over the start and end indices of subarrays. In some cases, you might use a temporary variable or array to extract subarrays for validation. To improve efficiency, certain optimizations can be applied. For instance, if a subarray fails the ascending check, the inner loop can exit early, saving unnecessary iterations. An advanced optimization involves using a sliding window technique to avoid recalculating sums for overlapping subarrays. This approach updates the sum incrementally as the window expands, reducing redundant operations. Additionally, instead of explicitly extracting subarrays using slicing, you can validate the ascending condition directly within the loops. This avoids the overhead of creating new arrays and reduces memory usage. Let's walk through an example to see the algorithm in action. Consider the input array nums equals 1, 3, 2, 4. The outer loop starts with I equals 0. The inner loop iterates over j from 0 to 3. For j equals 0, the subarray is 1, which is valid, so its sum, 1, is added to the result. For j equals 1, the subarray 1, 3 is also valid, and its sum, 4, is added. However, for j equals 2, the subarray 1, 3, 2 is not strictly ascending, so the inner loop breaks. Then, for j equals 3, after restarting, the subarray 2, 4 is checked and found valid, contributing another sum of 10. This process continues for all values of I, covering every possible subarray and summing the valid ones. At the end, the algorithm outputs the total sum of all valid subarrays. This Python implementation solves LeetCode problem 1800, maximum ascending subarray sum, using an iterative approach. The goal is to find the maximum sum of strictly ascending subarrays in a given list of integers. The max ascending sum function starts by initializing max_sum to 0, which keeps track of the maximum ascending subarray sum encountered so far. The current_sum is initialized to the first element of the array since we assume at least one number exists in the input. The for loop iterates from the second element to the end of the list. For each element at index I, it checks if the current number nums, I, is greater than the previous number nums, I1. If true, it indicates the ascending subarray continues, and we add nums, I, to current_sum. If the condition fails, the ascending subarray ends. At this point, we update max_sum by comparing it with current_sum and reset current_sum to the current number nums, I, effectively starting a new subarray. Finally, after the loop ends, there is a final comparison of max_sum and current_sum to ensure that the last ascending subarray is considered. The function then returns the max_sum, which is the maximum sum of all ascending subarrays in the input list. This approach has a time complexity of O(n), since we traverse the list once, and a space complexity of O(1), as no additional data structures are used. This is the Java implementation of LeetCode problem number 1800, maximum ascending subarray sum. The logic mirrors the Python solution, using a loop to iterate through the array, tracking the current ascending subarray sum, and updating the maximum sum when the sequence breaks. Key differences include explicit type declarations and the use of Java's math.max method for comparisons. The implementation ensures efficient traversal with O(n) time complexity. Here, we start with the first example where the input array is nums equals 10, 20, 30, 5, 10, 50. We initialize two variables, max_sum, which keeps track of the maximum sum of any ascending subarray, and current_sum, which starts with the first element of the array, 10. In the first iteration, we compare nums, 1, which is 20, with nums, 0, which is 10. Since 20 is greater than 10, the subarray is ascending, so we add 20 to current_sum. This gives us a new current_sum of 30. Next, in the second iteration, nums, 2, which is 30, is compared to nums, 1, which is 20. Again, 30 is greater than 20, so the subarray remains ascending, and we add 30 to current_sum. Now, current_sum becomes 60. In the third iteration, we compare nums, 3, which is 5, with nums, 2, which is 30. Since 5 is less than or equal to 30, the ascending subarray ends here. We update max_sum by taking the maximum of the current max_sum, which is 0, and the current_sum, which is 60. This updates max_sum to 60. Since the ascending subarray has ended, we start a new subarray with current_sum set to nums, 3, which is 5. Moving on to the fourth iteration, nums, 4, which is 10, is greater than nums, 3, which is 5, so the subarray is ascending, and we add 10 to current_sum. This gives a new current_sum of 15. Then, in the fifth iteration, nums 5, which is 50, is greater than nums 4, which is 10. The subarray continues to ascend, so we add 50 to current_sum, resulting in a current_sum of 65. At the end of the loop, we update max_sum one last time, taking the maximum of the current max_sum, which is 60, and the final current_sum, which is 65. This updates max_sum to 65. The output for this example is 65, as it represents the maximum sum of any ascending subarray. Now, let's move on to the second example where the input array is nums equals 5, 4, 3, 2, 1. We initialize max_sum to 0 and current_sum to the first element, which is 5. In the first iteration, we compare nums 1, which is 4, with nums 0, which is 5. Since 4 is less than or equal to 5, the ascending subarray ends. We update max_sum by taking the maximum of max_sum, which is 0, and current_sum, which is 5. This updates max_sum to 5. We then start a new subarray with current_sum set to nums 1, which is 4. In the second iteration, nums 2, which is 3, is compared to nums 1, which is 4. Since 3 is less than or equal to 4, the ascending subarray ends again. We update max_sum by taking the maximum of max_sum, which is 5, and current_sum, which is 4. Max_sum remains 5, and we start a new subarray with current_sum set to nums 2, which is 3. In the third iteration, nums 3, which is 2, is compared to nums 2, which is 3. Since 2 is less than or equal to 3, the ascending subarray ends. We update max_sum by taking the maximum of max_sum, which is 5, and current_sum, which is 3. Max_sum stays 5, and we start a new subarray with current_sum set to nums 3, which is 2. Then, in the fourth iteration, nums 4, which is 1, is compared to nums 3, which is 2. Since 1 is less than or equal to 2, the ascending subarray ends once more. We update max_sum by taking the maximum of max_sum, which is 5, and current_sum, which is 2. Max_sum remains 5, and we start a new subarray with current_sum set to nums 4, which is 1. At the end of the loop, we perform one final update to max_sum, taking the maximum of max_sum, which is 5, and current_sum, which is 1. Max_sum remains 5, and the output for this example is 5. Now we look at the third example where nums equals 1, 2, 3, 4, 5. Again, we initialize max_sum to 0 and current_sum to the first element, which is 1. In the first iteration, we compare nums 1, which is 2, with nums 0, which is 1. Since 2 is greater than 1, the subarray is ascending, and we add 2 to current_sum. This gives a new current_sum of 3. In the second iteration, nums 2, which is 3, is compared to nums 1, which is 2. Since 3 is greater than 2, the subarray continues to ascend, so we add 3 to current_sum. Now, current_sum becomes 6. In the third iteration, nums 3, which is 4, is compared to nums 2, which is 3. Since 4 is greater than 3, the subarray is still ascending, so we add 4 to current_sum. This updates current_sum to 10. In the fourth iteration, nums 4, which is 5, is compared to nums 3, which is 4. Since 5 is greater than 4, the subarray continues to ascend, and we add 5 to current_sum. This results in a current_sum of 15. At the end of the loop, we update max_sum one final time by taking the maximum of max_sum, which is 0, and current_sum, which is 15. This updates max_sum to 15. The output for this example is 15, which represents the maximum sum of the ascending subarray 1, 2, 3, 4, 5. In analyzing the time complexity of our solution, we begin by noting that the algorithm processes the input array nums using a single for loop. This loop starts at index 1 and iterates through the array up to len nums 1. Before the loop, we initialize two variables, max_sum and current_sum. These assignments require constant time, or O1. Now, during each iteration of the loop, we perform a comparison to check whether the current element is greater than the previous element. This comparison is a constant time operation, O1. If the condition holds true, we add the current element to current_sum, which is also O1. If the condition is false, we update max_sum and reinitialize current_sum, both of which are constant time operations as well. Because the loop iterates n1 times, where n is the length of the array, and each iteration involves a fixed amount of work, the total time complexity of the loop is proportional to n. Finally, after the loop, we perform a single max operation to finalize the result, which takes constant time. Altogether, the time complexity of this solution is O(n). When we combine all the steps, the overall time complexity of the algorithm is O(n). Now, let's examine the space complexity. The algorithm uses only a constant amount of additional space, regardless of the size of the input array. Specifically, the input array nums is read-only and does not contribute to the space complexity. We use two scalar variables, max_sum and current_sum, which each consume constant space, or O1. No additional data structures, such as arrays or lists, are used, and the solution does not rely on recursive calls. As a result, the total space complexity of the solution is O1. This makes the algorithm not only time efficient but also highly space efficient. To better understand the efficiency of our optimized solution, let's compare it to a brute force approach. A brute force algorithm would involve generating all possible subarrays, verifying if each subarray is ascending, and calculating the sum for those that meet the condition. Specifically, this would require iterating over all potential starting indices of subarrays, taking O(n). For each starting index, we would iterate over all possible ending indices, which takes O(n) in the worst case. Finally, for each subarray, we would check if it is ascending and compute its sum, taking O(k) time, where k is the length of the subarray. Combining these steps, the total time complexity of the brute force solution becomes O(n) cubed, in the worst case, where n is the size of the input array. By contrast, the optimized solution processes the array in a single pass, avoiding redundant computations and reducing the time complexity to O(n). This represents a substantial improvement, making the optimized approach far more suitable for larger input sizes. Finally, let's analyze the algorithm's behavior across different scenarios. In the best-case scenario, where the array is strictly ascending, such as 1, 2, 3, 4, the loop simply accumulates the sum without needing to reset current_sum. Even in this case, the algorithm still performs one pass through the array, so the time complexity remains O(n). For a typical input array with random values, which represents the average case, the loop will occasionally reset current_sum when the ascending property is violated. However, since the number of operations per iteration is constant, the time complexity is still O(n). In the worst-case scenario, where the array alternates between ascending and descending values, such as 10, 1, 20, 2, 30, 3, the algorithm resets current_sum at every step. Even under these conditions, the total time complexity remains O(n), because the loop iterates through the array just once. To confirm this mathematically, the loop runs n1 iterations, with each iteration performing a constant number of operations. Therefore, the total time complexity is O(n). As for space complexity, it remains O(1), because the algorithm uses a fixed number of scalar variables, regardless of the size of the input array. When working on this problem, there are a few common mistakes to watch out for. First, misunderstanding the problem constraints is a frequent issue. For instance, some candidates overlook edge cases like empty arrays, arrays with just one element, or those containing negative numbers. It's important to carefully review the constraints, such as the size of the input array and the range of possible values, before finalizing your approach. Additionally, inefficient approaches can be problematic, especially for large inputs. While brute force might seem tempting, it becomes impractical as the input size grows, particularly when the array length approaches 10,000. Scalability should always be a priority to avoid time limit errors. Another common mistake is off-by-one errors when defining the bounds of subarrays. Small indexing mistakes can lead to incorrect results or overlooked subarrays. Lastly, overcomplicating the solution can cause unnecessary difficulties. Adding extra nested loops or data structures often increases complexity without adding value. Always aim for simplicity and correctness in your logic. Failing to validate assumptions is another critical mistake to avoid. For example, assuming the array is sorted when the problem doesn't specify this, or neglecting to test edge cases like arrays with duplicate values, can lead to incorrect solutions. Now, when it comes to interview scenarios, there are a few key insights to consider. First, pattern recognition is essential. Many array-based problems require identifying patterns such as monotonic sequences, sliding windows, or prefix sums. Spotting these early can guide you toward efficient strategies. It's also important to communicate trade-offs clearly. Interviewers value candidates who can start with a simple brute force approach and then optimize it, demonstrating a clear problem-solving progression. Handling edge cases effectively is another skill interviewers look for. For instance, you should confirm how to handle arrays with duplicates or zero-length arrays. Finally, optimizing your solution using techniques like two-pointer methods, dynamic programming, or binary search can make a big difference in both efficiency and clarity. Some related problems that can help you deepen your understanding include LeetCode 53, Maximum Subarray, which focuses on finding the largest sum of a contiguous subarray, and LeetCode 152, Maximum Product Subarray, which extends this idea to products instead of sums. LeetCode 560, Subarray sum equals k, is another relevant problem where you count subarrays with a specific sum, and LeetCode 209, Minimum Size Subarray Sum, which challenges you to find the smallest subarray with a sum greater than or equal to a target value. In terms of alternative approaches, sliding window techniques are particularly useful when dealing with contiguous subarrays. By dynamically adjusting the window, you can often reduce the complexity to O(n). However, this method requires careful handling of when and how the window expands or contracts. Another approach is the prefix sum technique, which simplifies subarray sum calculations to O(1) once you've pre-computed the cumulative sums. The trade-off is that it requires additional space to store these sums, but it's highly effective for problems involving range queries. Dynamic programming is another powerful approach for solving problems like this, especially when the problem exhibits optimal substructure and overlapping subproblems. While it often involves higher space complexity, it provides clarity and ensures correctness, making it a reliable choice for more complex scenarios. Finally, the divide and conquer technique can be useful for problems that can be broken into smaller recursive subproblems, such as finding maximum subarray sums. This approach leverages recursion but introduces an overhead that can make it less practical under strict time constraints. It's also more challenging to implement correctly, so it's best reserved for scenarios where recursion is a natural fit for the problem structure. By understanding these techniques and their trade-offs, you can choose the most appropriate method for the given constraints and requirements, ensuring both efficiency and accuracy in your solution. Great job! We've tackled problem number 1800, Maximum Ascending Subarray Sum. We summarized the key concepts, the importance of optimization, and the takeaways from solving this problem. If you enjoyed this session, make sure to stay tuned for more coding solutions. Thank you for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!